Welcome to Ready to Derive. In this video, we are not going to be diving into examples as we usually do, but instead just going to look at the theoretical approach to volume using calculus. And we do this by linking it back and revisiting how we learned about finding the area under the curve using a definite integral. In the same way we used Riemann sums back then, we will be using Riemann sums to find the volume of a solid. So without further ado, let's get started. So before we get into deriving the volume formula using calculus, we're going to revisit how we came up with the formula for the area under a curve, because the parallels are very helpful. So imagine, let's go back to when we tried to find the area under a curve from A to B, and let's just call this f of x. And if you recall, before we knew about anything about integrals, we did this by using rectangles. So we would approximate the area under the curve by creating rectangles and finding the area of the rectangle. So these could be left endpoint rectangles, for example, but they could have been right endpoint ones, and adding those up all the way from A to B. And if you recall, so if we just, let's have a look at a typical one. The width of the rectangle we could calculate as, and we called it delta x, and that would just be given by the difference b minus a divided by the number of rectangles we want. And then the height, we could just call it, it would just be f of whatever particular value we were using. So in this case, the left endpoint, we just call it xi. So the area under the curve could be approximated, so very important that we see the approximation sign, by the sum of all these areas. And let's just have a look. F of xi is just the height of any one of these rectangles, and delta x would be the width. And how could we improve this estimate? Well, that would be by increasing the number of rectangles. If we increase the number of rectangles, then delta x, the width of each rectangle, will get smaller and smaller, and the approximation will get better. In fact, if we send n to infinity, then we would actually be able to get the area, even though we really don't want to be adding up the area of infinitely many rectangles. So, but this is where calculus came in. So what is this limit? This limit is defined as the definite integral from a to b of the function f of x with respect to x. And if we kind of, let's just get rid of these rectangles now, because it's helpful to think about, so what's the dx? The dx comes from the delta x. It's what happens as n goes to infinity. Delta x tends towards 0, and it becomes represented in the integral sign as dx. So it's almost like this. You could imagine it as having a rectangle that's infinitely thin. Dx stands for sort of an infinitesimal, and the height of that rectangle is f of x. It's not really a rectangle, it's really more like a line segment. And what the integral sign does, because the integral sign is really the summation as n goes to infinity, the limit of that summation, it's almost as if you are just, if you think about it, f of x, it's just a y value. It's almost as if you're just, the integral sign just adds up every single y value from a to b. Now that's pretty profound, because that could take, well, that would take forever by hand. But as you add up all those y values, you sweep out the region under the curve and you get the exact area. So keep this in mind as we move into applying this to finding volume. So there is a formula we have to review before we get into the calculus, and that's the volume of a prism, which many of us will not have seen since geometry. And a prism is any object in which you have congruent faces. So the top and the bottom of this are congruent. And in fact, if you cut the prism horizontally parallel to any of the bases and you open up and look at the cross-section, it will be congruent to the top and the bottom. So it has to be a uniform shape all the way through the prism. And if we recall that the volume of a prism is just the area of the base times the height. So if we say that B is the area of the base, I know that looks like the top, but remember that would be the same area as this. The area of the base times the height of the prism is the volume of a prism. And this, hopefully this makes sense to you. If I, let me just extract that base out. So that's the area of the base, B. So let me put B there. And just imagine how you create this prism. You just take those bases, same congruent shape, and stack it on top of one another. So obviously the area of the base and then times the height, because that's how many stacks we'd like to get in there, and that would give the volume of a prism. Now, this is a loaf of bread. Yes, this is quite a surprise. I'm sure you weren't expecting this. A loaf of bread is not a prism, so we need to be clear on that, because as we know, a loaf of bread, they're similar shapes, the slices, but they kind of tapers towards the end. So we can't use this formula for the volume of a loaf of bread, but we can if we just look at one particular slice. So if we think about it, let's look at just even the end slice. You can think, for all intents and purposes, you can think of the area of the base to be B is the area of the base, and the height would be the width of that. And it would be an approximation because it's very irregular shaped, but you could work out the volume of one of those slices. So the volume of this slice, again, you take the area of the base there, and you'd multiply it by, this would be, well, delta x is what we called it before, and times the area of the base there, which is the face of that slice, and that would give us the volume. And why does that matter? Because then, in the same way that Riemann Sums estimated the area under the curve, we could chop up a solid into slices, like we were slicing a loaf of bread. If we could work out the volume of one of each of those slices and add them up, then we would be able to estimate the volume of the solid. So here is a three-dimensional solid, an uncut loaf of bread, and we are going to think about, what we did in the last slide, think about cutting it up into n slices. And if we cut it up into n slices and looked at kind of a representative slice, let's see, might go like this. It's and then in the back, it's kind of a little hard to represent, but we can see it kind of that slice of bread looking like this. And if we find the area of the face of a slice of bread, and then if we cut it, say this thick, so this would be, that would be delta x. That will depend, delta x will depend on how many slices we cut. Then we know that the volume of one slice, because we can sort of treat that like a prism, a very thin prism, the volume of one slice will just be the area of the face of the slice times delta x, the height of it, or the width. And so if we want the volume of an approximation of the volume of the loaf, we would just add up the volumes of all those slices, kind of like we did. This is a Riemann sum, but in terms of volume. And if we want to improve that, then of course we cut the slices thinner and thinner by cutting more of them. In fact, if we let n go to infinity, so if we cut infinitely many slices, then the volume, it would be exactly the limit of this expression. And it's not hard to see how then this morphs into the definite integral. Once again, as n goes to infinity, delta x goes to 0 and is represented by dx. So that would be the slice. That's a slice where it's literally just, it's like paper thin slice. That would be a paper thin slice like this with a width of dx, whatever width, that's not even barely a width, it's just representative of width, and the area of the face. So once again, it's almost like you're just adding up area of infinitely many faces all the way from A to B, and it has to be, so the only thing I'm missing from here is that you just have to imagine that the x-axis is kind of coming up out like that, and the y-axis is heading up there. And so this formula, this definite integral, will give us the volume of any solid. So as long as we can define a of x throughout the solid, as long as we can find a formula for the area of a cross-section, we can find the volume. So just to recap, if we would like to find the area under a curve, say from A to B, say that function is f of x, and we know that that is the definite integral from A to B of f of x dx. Think of this formula as saying that what you're basically doing is you're adding up all the line segments from A here, every single value of f of x. You're sweeping out the whole area of the region all the way up to B, and the integral sign is doing that for you. So from A all the way up to B, adding up every single y value thanks to the integral. In the same way, if we would like to work out the volume, so let's just create a three-dimensional solid. So if we'd like to work out the volume of this solid from A, say to here, to B, then the volume in the same way is the definite integral from A to B of the area of the cross-sections with respect to x. And so an area of a cross-section could look like this here, right? So this would be A of x in that position, and at any position A of x is going to vary because it's a function of x. And if we add up all those areas from all the way from A, which is virtually nothing, to B, so to these, this is a vase on its side, we add up all those areas, we sweep out the whole volume of the solid. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.